All right. Hello, everyone. So, welcome to my stream. I appreciate the 7 of you right now who hopped on stream, even though I just randomly started at 11:45. I'm usually trying to do these things on Wednesday around 11. Technical issues often hold me up and whatnot. So, yeah, there we go. So, let's see. Today we're going to be talking about some operator theory and other things like that. This is in support of a textbook that I'm putting together, so on data-driven methods in dynamical systems, functional analysis, and operator theory, and all that stuff. And I want to be really cohesive in the book, so I'm going to go and start at the beginning of operator theory, build up to a lot of concepts, things like that, so that we can talk about things like dynamic mode decomposition, ridge regression, all these other things in a very mathematical way. And so thank you. I don't know. Last time I had the stream, I had horrible frame rates for the video. I think I fixed that part. This is my second time really streaming with this sort of thing. Well, at least this year. I streamed 2 other times other than that, so I'm very new to this. But I appreciate the support. Yeah, it is going to get complex eventually, but today it's going to be pretty basic. So we're going to talk about operators, bounded operators over Hilbert spaces, things like that. So should be pretty fun. Let's see. So let me go ahead and pull up the tablet screen so we can see what we're dealing with. So this is what we got. So I'm going to be talking about, I was calling this lesson 1 aspirationally, so hopefully we'll be able to do this on a weekly or a semi-weekly basis. And today we're just talking about boundedness over Hilbert spaces. So we're going to have a little bit of content from Hilbert spaces. I'll talk about some of the preliminary stuff we're going to be needing from there, but I'm not going to develop all that stuff from scratch here. I have a whole bunch of other YouTube videos and stuff like that, which I'm sure some of you have already seen. But we'll talk about the theorems that we need and the basics that are coming out of there. So we're going to start off with a discussion of preliminaries with Hilbert spaces and whatnot. And also introduce a bunch of reproduced kernel Hilbert spaces as we go and just talk about what that is. Because it's really nice to see a lot of these interactions with kernel functions and operators. So let's see. Then we'll just go through definitions of a linear operator over a Hilbert space. And honestly, these definitions can often be extended to norm-vector spaces or Banach spaces or even topological vector spaces. But we're going to be mostly concerned with Hilbert spaces because we're going to really like the interplay between the inner products and operators. So then we're going to go ahead and talk about the definition of bounded operators, and we're going to talk about the definition of a norm on an operator itself, which will actually give us what is called a Banach algebra. We're not going to go deep into what a Banach algebra is, but if you ever wanted to know more about it, let's this is the Bible of Banach algebras, and it's a really good book. I feel like I've never really had strong enough algebra to get through all of it, but mainly I lived on the last couple chapters on Topos operators and Hardy spaces, which were really fun. So it's a really good book by Ron Douglas. Met him once at a conference, said thanks for the book, thanks for writing the book, and yeah, because it basically helped me get my PhD done. Okay, so let's see. So looking at chat, what's the best way to study measure theory and functional analysis? I am taking a class in measure theory and just going over this great case of outer measures and its properties. Lots of unit sets. Honestly, that's a lot of the grunt work that goes into measure theory. Measure theory is one of these things that you study really hard in graduate school and you get really good at it. And for people who do functional analysis, you just know it's there and then you just move on. But if you really want to get solid at measure theory and things like that, really the best thing to do is just crack open a book, do lots and lots of exercises. Just get used to going over these things, and and just learning how to manipulate them. I personally have had a schedule when I was a PhD student studying for my measure theory exam. I was basically a PhD qualifier, which covered about an entire year's of material in about 6 questions. I spent 3 months studying like 5 hours a day for that class, or for that exam itself. I just spent the entire summer doing that, and I would basically wake up and, before having breakfast, before doing anything else, I'd sit down for a couple hours and go over a basic theorem that I'd seen the day before, look at problems I had trouble with the day before, things like that, and then go eat breakfast, do whatever, and then come back for another 3 hours session, and just crank out problems, see what proofs I could reproduce off the top of my head, and if I couldn't do it off the top of my head, I'd work on chunking them, turning them into little pieces inside the proof, and then I would try that again. And I did this every day for months, and so until the point where I just basically knew the book forwards and backwards. The book I was using is the one this was a book I was studying for measure theory. It's a really solid introduction, I think, and I like it better than Rudin's introduction and his real and complex analysis. And I also like it better than Halmos. Paul Halmos. Paul Halmos wrote the first measure theory textbook. It's a good textbook. He's a good writer, but I just prefer this one by Folan better. And so that's what I did. That's how I got through there. All right, let's see, another chat. I always hear about Hilbert spaces and quantum mechanics and linear algebra. Yeah, so quantum mechanics and operator theory are both extremely intertwined. So von Neumann, he basically solidified our notions of operator theory to just general Hilbert spaces outside of L2 and things like that in his works in, I think, the 1950s, 40s. I have to double check on that one. But basically, he wrote the book on quantum mechanics and operator theory. His book's pretty dense to get through, but if you want a really good introduction for that, I don't have a copy here, but there's Quantum Theory for Mathematicians by Brian C. Hall, I believe. And if you get that, it basically breaks down all the connections between functional analysis, Hilbert spaces, and Fock spaces, and just how all that interplays with quantum mechanics. It's a really good book. I recommend it. I actually, for my PhD students, part of their candidacy exam, I have them basically learn a lot of functional analysis from that book, because it gives them a splash of quantum mechanics and other things if they don't have it already, and it has a really great compact summary of the essentials of functional analysis, which I think is really good. All right. The overarching theme for measure theory, there's really 2 different directions that it goes. So on one hand, measure theory is created for the sake of doing Lebesgue integration and doing integration theory in general. And so, and that's really the value that we got out of it. So when you take a look at, people like Hilbert, when he was working on his initial Hilbert spaces, which is L2, there was a problem of, establishing completeness, and it just came down to the fact that L2 functions are very hard to integrate in general. If you have a continuous function, you can use Riemann integral, but if you have something that's just so simple as the indicator function for rationals, suddenly that's not amenable to Riemann integration. So we needed a new kind of integration theory, and that came from Lebesgue integration, which requires you to be able to take measurements of very weird looking sets. So no longer using a ruler on the interval, but rather you can have these sort of fractal like sets that you suddenly need to take a measurement of, and so, or a Cantor set, something like that. And so then that's when we started getting that's when we had the introduction of measures, and that's really what they're there for, is to do integration theory, basically supporting all the stuff that we're going to be talking about with L2 and other things sort of behind the scenes. Then later on, Kolmogorov, the Russian mathematician, super genius guy, made the connection that measures and probabilities are the same. And so he drew this connection, and then that allowed us to put a lot more rigor into probability theory and statistics. And so there's two different directions you can take then. So you can take measure theory to integration theory, or you can take measure theory towards statistics and probability. Personally, I went the integration route, and I know a smattering of things from probability theory, but nothing really too big. In probability theory, you're usually using finite measure spaces rather than like measures over Rn or R. Or well, I guess measures over Rn and R, but like Lebesgue measure, those sets can have measure arbitrarily large. But if you have a probability measure on R or Rn, then the most they can be is 1. So, but yeah, outside of that, I really haven't used measure theory outside of just setting up integration theory. For me, I went into functional analysis and complex analysis directions, and that's where I've lived. All right, so what math proof skills do theoretical and mathematical physicists use? So trying to learn how to write math proofs. Honestly, it really just depends on the physicists you're talking about. Mathematical physicists are often housed in math departments, so they do math proofs just like any other mathematician, somebody in functional analysis, and things like that. I've been told by a mathematical physicist that I basically do mathematical physics. I don't know enough physics to really do anything useful, so I mean, like, I just think I work on a lot of the objects that mathematical physicists also work on, which are Hilbert spaces and operators. And so in that sense, I'm sort of in that same realm, but I would never call myself a mathematical physicist. But the ones I do know, they do a lot of work in analysis and operator theory, and that's where they live. And then we have for theoretical physicists, they're a lot more loose. They're usually in physics departments. They will have generally a very strong idea of analysis and a lot of the things that they want to use. But you have a big spectrum there. You have some that are just absolutely rigid, like mathematicians, and others that will just sort of like sort of run by intuition a lot. I mean, even if you look at Paul Dirac, I mean, like when he came up with his initial bits of quantum mechanics, he introduced the Dirac delta function. But at the time, there was no mathematics really supporting the delta function. That didn't come for another like 15, 20 years. So, I mean, Dirac introduced his stuff, I think, in the 1935 or so. And then you had Lawrence Schwartz, in the 1940s, basically talking about what the delta function is, and as a distribution, and he introduced distribution theory. And Dirac, he got his Fields Medal, and his Nobel Prize in 1938, and Lawrence Schwartz, he got his Fields Medal in 1950. So let's see. Okay. Yeah, I love doing mathematics, and so that's what I like doing. So, but I'm happy to provide whatever information I can. We're all here to hang out and do some stuff, and hopefully we'll get to math eventually. All right, so let's go ahead and take a look. All right, so I last time I made this lecture, I had no idea what I was going to do. I was just like, I just need to jump in and do a stream and get it done. And so it was sort of all over the place. But here I'm a little bit more organized. I actually even worked out proofs ahead of time on my whiteboard. so I practiced, I'm ready, and so let's go ahead and get into this. So we're going to start talking about some prerequisites here. We're talking about Hilbert spaces. Now, Hilbert spaces, to start, before we talk about Hilbert space, we're going to talk about a norm vector space, because you have to know what a norm is to understand what a Hilbert space is. And so a norm vector space is a vector space V. It is equipped with a function, and this is what we call the norm. And so it's a function from the vector space to R+. So a norm is really just the length of a vector, if you wanted something like that. And so basically what we got is we have this nice property for a norm. So if you take elements of your vector space V and some scalars that are complex scalars, they can be real scalars too if you want, then what we can do is we say that the norm of a vector is always positive unless it's 0, and then the norm of 0 is just 0. And so that's more or less what you would expect, I think. And then here we have this property where basically it takes a scalar onto the outside as an absolute value. And so that's pretty nice. And then the last thing we want for a norm is this one, and this is what gives us a triangle inequality, which allows us to convert norms into metric spaces and metrics. And so with this, we have the triangle inequality, so the norm of the sum is less than the sum of the norms, or less than or equal to. And so that's all very nice. And then what we can do is we can take any of these guys and we can turn it into a distance measure. So we can say the distance between v and w is going to be v minus w. And that is a metric that we put onto our norm vector spaces. And so when you have the metric, then you can ask questions about completeness and whether or not if you have a sequence that looks like it's converging, that's a Cauchy sequence, does it actually converge inside the space? And that's what we get when we talk about Hilbert spaces. So a Hilbert space is a complete norm vector space. And if it was just a complete norm vector space, that's what we would call a Banach space. Now, here we have something extra. We have an extra structure for a Hilbert space, and that is this inner product. Inner products are just dot products, just like Rn's dot product. Rn's dot product is it is an inner product. And so here, this is just the more general term, inner product. And in this case, inner products allow us to do the same things that dot products do, and that is talk about angles. And so you can talk about things that are going to be orthogonal to each other or at right angles to each other. And that's when the inner products between those two elements is 0. And so, but in general, for an inner product, we have this. So if I take these three elements, f, g, and h inside of h, and I take my alpha and my beta inside of my scalars, we have these three properties. We have the inner product of f with itself is positive, and unless f itself is 0, and then the inner product of 0 with itself is 0. And this is really there just to test your this is just to test out, not test out, this is just to make a norm. And so we're going to be talking about this. This is going to give us a norm on our vector space. And so we also have this linearity property, which is pretty nice. So in the first term here, if we have alpha f plus beta g, then we can split these guys out here where we're keeping the h on the right hand side. Now, this only works for the left component. For the right component, it would come out as conjugate linear. So these guys would have bars on them if this was over here in this term. And that is because we have this, which is this conjugate symmetry. If you exchange f and g in your inner product, then it comes off with a complex conjugate. Remember, the value of this function is always complex. And so basically you have linear and the left hand side, and then you have on the right hand side is going to be conjugate linear. Okay, so when you have basically you have this thing that is called an inner product. The Hilbert space is a complete norm vector space equipped with an inner product, such that the norm itself is given by the inner product. So we can put inner products on spaces that aren't Hilbert spaces, but that inner product wouldn't necessarily be connected to the norm of the space. And so there's actually a few different ways you can take a look. You can start with a norm and you can build an inner product. That's actually an exercise that you'll see in, say, Foland, for instance. It's a great way to go. All right, let me check over chat. I've been ignoring it for a minute. Oh, you want me to turn off the music? Okay, yeah, we can turn the music down. Sure. Yeah, let's just turn it off. Just it gets rattly in the room here. But okay. Let's see. Okay, so I am reading Mathematics Signal Processing with Damelin and Miller. I am at the end section of Hilbert spaces L2 and little L2. Okay, cool. Yeah. Okay. Yeah, sorry about all the music. I'm sorry about that, guys. Um, yeah, and let's see. Okay, yeah. So little L2 and L2, yeah, they're great. We'll talk about them a bit. I've actually have a whole series of videos on the channel right now where I've been diving into just L2, and I have a video that's going to come out on Friday, I think, or maybe tomorrow. I haven't actually decided when I want to put it out. But it talks about establishing the Hermite functions as basis for L2, which is something that it took me a while to actually track down a decent proof for. Ultimately, I had to find a proof inside of here buried in the exercises, and so we go through that. I had another book on that. I had orthogonal polynomials that I was digging through, and it had a great proof, a very complete proof, but man, it took a long time, and I honestly don't want to go through that proof again. So the full-in proof actually works out a lot nicer. And yeah, so the question here was the inner product of 0 with itself equaling 0 does follow from 2, because then basically if we take any 0 times a vector, we can just pull it out by linearity. Then you have the 0 scalar times the function, and so that's that'll give you that indeed. Let's see. It's one, it isn't necessarily the completeness condition. You could have an inner product that isn't in a complete space, but this is more. This just allows you. It just makes sure that if you have this identification of, say, f minus g is equal to 0, which is what you would get if you use this as a norm. Then you want that to imply that f is equal to g. And so it does help with the completeness, but the completeness is a separate issue. Okay. So yeah, so basically what we want to be able to do is we want to turn this inner product into a norm. And if we have a norm, we want to be able to make sure that the norm tells us when things do converge, that is part of it. And so indeed, we want the norm to be able to give us identification. And so if the norm is if f minus g is 0, then f must be equal to g. You do need this if you want to use this for like sequences and convergence. But if the space wasn't complete, you could have a sequence that does tend to 0 inside the norm, but the ultimate function it converges to might not be 0. And so that's why you want this condition 1 here. Or well, no. So yeah, because basically you just need to fill in the holes. So just think of like the real numbers. We can have a norm that we put on the rational numbers that works out just fine, but we can have convergence inside the rational numbers to say square root of 2, and that would be a gap in the completeness. So even though we'd have a very nice inner product on the rationals, you wouldn't be able to necessarily go to square root 2. In this case, it would be a little bit more complicated because we would have to have a vector space that is over the rationals rather than over the complex numbers. Because yeah, sure, absolutely. I guess I'm rambling a bit too. Okay, so this is just something you would want. All right, so some examples. So we have 2 different Lebesgue spaces that we're going to be that we ultimately will talk about. Honestly, there's like a third one that we can talk about too. I'll add that in here in a second. But we have the Lebesgue space of 0, 1. And so this is a set of all functions over the interval 0 to 1 to the complex numbers, such that their square the integral of their square over the finite interval there is going to be finite. And then you can exchange that interval for the reals, and you get the same inequality, but just over the entire real line rather than just that interval. What's significant about these two guys, I mean, they both have the same inner product here, and so A and B, it could be 0, 1, or it could be minus infinity to infinity, depending on the context. But each of these spaces really behaves very differently. So in L2 of 0, 1, you can they have polynomials, and those polynomials can approximate any other function inside of L2, and you can, and that's very nice. But in over the reals, no polynomial is inside of L2, and that's just because they blow up to infinity as you go off to infinity, right? And so what we do in order to get a control of that is we often multiply that by a Gaussian to sort of like smash down these polynomials as you go off to infinity, and this is what gives us Hermite functions. So I have a whole series of videos I've been making on Hermite functions. If you'd like to learn more about those, they're very convenient as a basis and a great way of talking about the Fourier transform. There is the sequence space, little L2 of n, and this there we go. And this is basically the space of sequences an, and say going from 0 to infinity, such that the sum of an squared is less than infinity, n equals 0 to infinity. So that's pretty nice. And in this case, the inner product between two sequences is going to be the sum of an bn bar. And so that's very nice. So that's little L2 of n. Turns out that every separable Hilbert space can be compared to little L2 of n, and that's because every separable Hilbert space has a countable basis, and so then basically or a countable orthonormal basis, and so then basically what you need to do in order to get a correspondence between any separable Hilbert space and little L2 of n is that you just basically take the coefficients that you get off of your orthogonal expansions, and then you just cram them into a sequence, and then you call that your little L2n space. So okay, so those are Lebesgue spaces, little L2, things like that, which are all great. These were all introduced by Hilbert back in the late 1800s, and it was worked on by other people like Maurice Fréchet, and I think Sturm Liouville came in there as well. They were working on problems on like integral equations and differential equations and things like that, and so it was pretty nice. We had Maurice Fréchet came in, and he introduced the Riesz theorem, which we'll talk about in a second, and then Riesz himself came in and he scooped Maurice Fréchet on that just by a little bit. They were working together. It's just Maurice Fréchet. They were corresponding with each other, and apparently Maurice Fréchet was like working on this and submitted the paper at the same time that Riesz did, though Riesz didn't know that Maurice Fréchet was working on that particular problem, and so they both sort of converged on this separately and did it. So interestingly, every single Cn is itself a Hilbert space, and so it's it's a sort of mini version of our sequence space L2, little L2. Instead here we just sort of end it at say n. And so it has the same inner product, and this you'll notice is just the dot product from Cn or Rn if you just remove the conjugate there. But what's really neat is that you can also think of this as a function space, where it's a set of functions on a finite set of points. And so in this case, the inner product just becomes this. And so those two are actually equivalent spaces. And then this function space over finite sets is also a reproducible kernel Hilbert space. And so we'll talk about that and what that means in a second. Yeah, poor Maurice. He got scooped on a lot of stuff. He basically invented topology and then didn't get any credit for it. Feel bad for the guy. But apparently he's a nice guy. I don't know. Yeah. Anyway, so here we have two theorems from Hilbert space theory we're going to need. One is the Cauchy-Schwarz inequality. This one comes up quite a lot. And it's basically how you navigate around with inner products. And so it turns out that if you take the inner product with f and g, that is going to be less than or equal to the product of the norms. And so that's pretty nice. And then we have equality between the two only when they are sort of parallel. Parallel, it means basically they are the same except for the multiplication of a complex conjugate or a complex scalar. And so, yeah. So if this happens, then you have equality, and otherwise you have this inequality. This is Cauchy-Schwarz inequality, and I think it came about 1830 or so, something like that, 1840s, with Cauchy, and I'm not sure how Schwarz fit in there, but I forget which one. I think maybe Schwarz put in this for integration, and Cauchy did it for like sequences or like real numbers, etc. I don't know. I'd have to double check. Don't quote me on any of that. But yeah, but that's basically the idea. And then as far as linear functionals go, this is our first sort of like mini operator. So you can think of linear functionals as sort of our linear operators that map you from your vector space to a space of scalars, or to like the one-dimensional like a vector space R or C. And so in this case, we have our bounded linear functional on our norm vector space V. It's this mapping T that goes from V to C, and such that basically it's linear. That's what this means. So it satisfies this superposition property. And so T of alpha V plus beta W is the same as alpha TV plus beta TW, which is nice. And so this could work as a definition of a linear functional, but we want them to be bounded, and the bounded ones are ones that we really care about. This is what we use in, say, distribution theory. This is what we use when you talk about dual spaces, etc. And so it turns out that they have this property too, where basically the absolute value, because this is a real number, or a complex number, the magnitude of TV is less than or equal to some constant times the norm of V. And so it kind of doesn't, so as V goes to 0, this is going to go to 0 too. And so they sort of like are kind of co-measure it in a sense. And so, and this inequality is something we're going to see for bounded operators. And in particular, after we get our definition of a bounded operator, what we're going to see is that a linear functional is basically a bounded operator between two different Hilbert spaces, where one Hilbert space is this. But linear functionals are just used all over the place, and so it's good to single them out, and in particular because you get what is called the Riesz representation theorem, or the Riesz theorem, however you want. And so initially, like I said, this was due to Maurice Furchet and Riesz. In the case of big L2, the Lebesgue space, I think Riesz later on in the 1930s, he released a much more general version of his theorem, and for general Hilbert spaces. And so, but basically what this says is that if T is a bounded linear functional, and so satisfies that whole thing where we had magnitude of TV is less than or equal to C times norm of V, then what we end up having is that there's going to be some element of say G inside of our H, such that this whole linear functional can be represented just through the inner product, which is pretty nice. And so essentially what this tells us, and this is a very, very special case, is that all of our bounded linear functionals are essentially just elements of H put inside of an inner product. And so we have this direct correspondence between linear functionals and elements of H. And so this is very unusual. And so this collection of functionals, bounded linear functionals, form what we call a dual space for norm vector spaces, which can generally get to be larger than the space itself. But because it's a Hilbert space, the Riesz theorem tells us that it doesn't get any larger, and in fact, it is the same space again. And so this is very special for Hilbert spaces. Okay. So yeah. So that's basically a lot of the things we're going to want from basic Hilbert space theory. But I also want to tell you about reproducing kernel Hilbert spaces because, well, one, it's how I make all my money. I got employed because I do a lot of weird stuff with reproduced kernel Hilbert spaces and operators, and they're also used a lot. And so these are some examples of reproduced kernel Hilbert spaces. You've probably seen a bunch of examples you've seen these examples in other places before, I'm sure. So for instance, we have the Hardy space. The Hardy space itself is a collection of functions on the unit disk of the complex plane, and these, the easiest way to define them is this way: is we take basically any function, we look at it power series as representable as a power series, and we say that the coefficients from that power series are, you know, square summable. And the inner product here is just the same as what we had for little L2, and so this is actually just a collection of generating functions for sequences in little L2, and that's one way of looking at this. Another way of looking at it is that we have this inequality for the norm here, where basically the norm can be replaced by this, where we take the supremum as r goes, oh, not to infinity. That's wrong. Where'd my notebook? There we go. Sorry, you just saw some of my research, I think. Anyway, this goes up to 1 there, and yeah, and so that's another way of defining it. So you can start either with collections of analytic functions and controlling and looking at their coefficients, or you can look at them as functions of the disk that are analytic, and then that have this basically this inflation that you do here. We're basically going to be taking this r and letting it go up to 1 from 0, and basically taking and just seeing that the integrals around each of the circles, because that's e to the I theta in there, stays finite, square integrals of that. And when that happens, that also gives you the same norm and the same space. And so sometimes it's convenient, usually it's convenient to work with this norm, but other times when we talk about some operators, it'll be easier to use that one. Okay. Yeah, right. Yeah. So I guess I just leaked those notes. I don't know what notes I showed you. I have a bunch of random notes here on my tabs. I probably should have closed them beforehand. But yeah, yep, that's how it goes. G is, all right. So the question earlier, I'm sorry, I guess I missed this. Is G the kernel? No. In this case, it will be the kernel in a specific context. It is how we get kernel functions, and we'll see that coming up soon. But yeah, so G isn't kernel yet, but it will be in a particular application. And yeah, honestly, yeah, reproducible kernels, they make money. I mean, this is a lot of the heart of machine learning and all that other stuff. And so classification problems, and all these other things all came from reproducible kernel Hilbert spaces. So we had support vector machines, and that was done in the 1980s and 90s. That was a big money generator, and that's how a lot of things got started there. Yeah, I don't know. I have brought in personally about $1.5 million of federal funding for my research program. I mean, it doesn't go to my bank account, which would be nice, but funds my students and other things like that, travel, etc. And that was all on the back of reproducible kernel over spaces and operators. And eventually, I'd like to get to a point where I can talk to you about some of that work too. Okay, sorry, keep getting distracted. I don't know the balance between checking chat and just giving my lecture. I'm happy for any questions anybody wants to ask. That's more than welcome. I just need to get better at hopping between these two. But yeah, so another space that we want to talk about here is the Fock space. Again, there is also an integral representation of this, but I'm just going to ignore that because it's not going to be relevant for most of the things we do. The Fock space is also known as the Siegel-Bargmann space. Siegel-Bargmann space. The Siegel space, the Bargmann space, the Fock space, the Siegel-Bargmann Fock space. Just these three guys kind of worked on it separately, and it all sort of came together. Fock himself came in from quantum mechanics, and that's where he did a lot of his development. And whereas the Bargmann himself looked at this from the perspective of spaces of entire functions. And so the Fock space in particular is directly connected to the quantum harmonic oscillator, and one day we can come back and talk about that, but that's not what I'm going to talk about. Again, if you want to see what that's about, Brian C. Hall's book, Quantum Theory for Mathematicians, really dives into that connection, which is very nice. Now, this last space is the Paley-Wiener space, and so the Paley-Wiener space is basically the space of band-limited functions. And so we fix some sort of band alpha that we want to stay within, and so some sort of like maximum value for our band. And this space is, it's very nice in a lot of ways. One, the inner product is basically the L2 inner product here, but just on the Fourier transforms instead. And yeah, essentially, basically, it's functions inside of L2, such that the Fourier transform vanishes outside of some fixed alpha band. And what's nice, though, is that while L2 members of L2 aren't actually functions, but they're rather equivalence classes of functions, Paley-Wiener functions can actually be viewed as just proper functions. And the route for this is straightforward, but basically you have that you just need two facts. One is that the Fourier transform of an L1 function is continuous, and so you have that. And so what you get here then is that the Fourier transform of f gets you to this compactly supported this Fourier transform. The spectral content is all contained within some finite bound, and it turns out that if you take an L2 function and you restrict it down to a compact set and you zero out everything else, then that is actually also an L1 function. And then if we take the inverse Fourier transform of that, it'll get us back to the original f, who is now seen as the Fourier transform applied to an L1 function. And so hence you get continuity. In fact, you get a lot more than continuity out of this. F turns out to be a real entire function, or an entire function on the real line. And that's because of the compact support. And so you can do a lot more than that, but my 2-minute explanation for the continuity and just justification of it as an actual function, that's what we got. It has to do with Fourier transforms L1 functions are continuous, and also if you zero out everything of an L2 function outside of some sort of compact interval, then that becomes an L1 function, and then inverse Fourier transform to get back. Yeah, I thought it was kind of fun, putting that together. Yeah, so the Paley-Wiener space, I actually didn't really work on it too much until I became a professor. It was something that sort of in the background that I knew about that I never really worked with. But lately I've been trying to do some work with it and some of the operators I work with lately. And so it's nice. But in particular, this is a space that gives you the Shannon-Nyquist theorem. And we can talk about this someday too. Okay, so I guess I've been chatting a lot more than I thought I would. I'm probably going to have to end the stream probably around 1 o'clock or so. But we'll see where we get to. And if we don't finish everything today, we'll just pick it up again next week or the week after, however my schedule works out. But okay, so reproducing kernel Hilbert spaces. These are my bread and butter, like I said. And so a reproducing kernel Hilbert space, this H over set X is a Hilbert space of functions from X to C. And so we have, but it's more than just a Hilbert space. You also have this functional called the evaluation functional as f mapping to f of x. And we declare that this linear functional is bounded. Now what's significant is that this means that we can't look at L2 as itself being a reproducible kernel Hilbert space, because function evaluation at a point does not make sense for L2 functions, because they are sets equivalence classes of functions that can differ at on measure zero sets, which includes point sets. So there is no sense of a value of a member in L2. They only make sense underneath integrals. So these require different kinds of functions, and so the Hardy space is reproduced kernel over space, the Fock space is reproduced kernel over space, the Paley-Wiener space is also a reproduced kernel over space, but L2 is not. And so, but since we have the bounded linear functional, that this evaluation is a bounded linear functional, what we get then is that there must exist some kx. This is our reproducing kernel to that question you asked earlier. And it turns out that f against kx is equal to f of x. And so this is our reproducing property. And this is called the reproducing kernel centered at x. And so the overall, so we have, this is the reproducing kernel centered at x. And then this is what we call the kernel function for h. And it turns out this is what we call a positive definite kernel, and if you have a which satisfies a certain matrix definition, and you can start with that matrix definition and cook up a reproduced kernel Hilbert space anytime you have that, where so this ends up being a unique correspondence. It's the Ehrenstein-Mohr theorem from, I think, 1950, if I remember right. So yeah, we can go through that some other time, but like I said, today, eventually, I'd like to get to talking about operators. But I just we need to talk about the spaces that we're working on before we can actually talk about operators and give some examples. All right, so these are the kernel functions that you have here. So this is called the Szego kernel, or Szego kernel. It is 1 over 1 minus w bar z. And so this is a kernel function for the unit disk. And so basically your center, this would be your w, and then you have that. I have a couple of videos on my channel that talks about the Hardy space and things like that. I have some nice pictures of what these things look like. As a function, you see that this is an analytic function, and w has to generally be less than 1 in magnitude. What ends up happening is on the reflection here is that this guy has a pole over on the other side. So the closer that gets to the boundary, you have a pole coming from the other side that's going to sort of push you up over there. But yeah. Significantly, the kernel corresponding to 0, for instance, is just the function 1, and so it's completely flat. And so as you get close to the origin, you sort of flatten out, and as w gets to the edge, you're going to start warping up on the disk. The Fock space, these are also known as coherent states for the quantum harmonic oscillator, but it's the exponential function, which is pretty nice. Now I invented another space called the Mittag-Leffler space, where the kernel function is actually the Mittag-Leffler function, and this works for like fractional differential equations, things like that. So then for that space of functions that work over a finite domain, this is just turns out the Kronecker delta function is what gives you your reproduced kernel Hilbert space. It gives you your kernel function, which is pretty nice. And this one, I know I messed up these coefficients. Sorry about that. But the Paley-Wiener kernel itself is a sinc function, and so that's pretty nice. And so when you see the Paley-Wiener space and the Shannon-Nyquist theorem, Shannon-Nyquist theorem says that you can basically reconstruct perfectly any function given that you are sampling at twice the highest frequency in the spectrum, right? And the way you do that reconstruction is through a linear or a series of these sinc functions. It turns out with just the right spacing of x and y, these sinc functions actually also turn out to be orthogonal, and that's because their Fourier transforms are basically just exponential functions restricted to an interval. And so you basically just tune those complex exponentials until you like turn them into sines and cosines that sort of annihilate each other. And so and that gives you the exact right spacing for this. It's pretty nice, but again, we'll talk about that later. Yeah, so So then that is, basically reproduce kernel Hilbert spaces. And let's talk about operators. All right, so here I'm actually going to start writing. I actually kind of ran out of time right before this. And so basically what we have here is we're going to go over the definition of a linear operator. So basically given a Hilbert space H, and all right, a linear operator T, which will map from what we'll call the domain of T to H, operator is a function that satisfies, say, for f and g inside of our domain, which is a subset of H, and two scalars alpha and beta. In C, we have this T of alpha F plus beta G is equal to alpha TF plus beta TG. All right, so really basic there. Not really a whole lot I'm saying. That domain T could be anything. It could be all of H, and that would, and it is in a lot of cases when we're talking about bounded linear operators. Often you will also have a dense subset of your Hilbert space that you'll actually care about. So you might be able to define a linear operator on just the polynomials, and then you just hope that later you can complete it to everything else, but just at least on the polynomials, and then those are dense inside the Hardy space and the Fock space, and so that's something you can do. So for instance, I can define this operator ddz, and this one we're gonna now let's just give it over, say, H2 of the disk, or the Hardy space. And so in here, it does what you think it does. But we still need to define, in order to be proper, a subspace of H. And so this, what I'll do right now, I could define this to be the set of polynomials, and then we would work off of that. But I can also give a sort of like cheeky definition, where I can say, let's say that this is the collection of f's inside of H2, such that the derivative of f stays in H2. All right, and so it's a little cheeky because, I mean, basically that's kind of what we're saying that operators should be doing, but I'm just saying basically take any function that in H2 that this will work for, throw that in a domain. And other times, they're just going to turn out to be some of these guys that aren't going to work out. So this won't be all of H2. And so, for instance, ddz, I could put it on z to the n, and that would give me n times z to the n minus 1. I mean, this is just a derivative operation. We know what this is. But if I apply it to another operation, so I can have, if we take, if f is, say, the sum of 1 over n times z to the n, then I know that sum of 1 over n squared is equal to pi squared over 6, which is finite. N equals 1 to infinity. And so that's in the Hardy space, but f prime is going to be z to the n equals 1 to infinity. Okay, well, that's fine, I guess. No, that's not fine. Actually, it's not fine. What am I saying? This is 1 over 1 minus z, but our coefficients in this case are just the constant 1. So we have just 1s here. And so the idea there is that this is infinity. And so the derivative operation isn't well defined for all of H. H2 or all of my Hardy space. And so we're not going to define it over the entire Hardy space, but we can define it on nice subsets with like polynomials, right? And so at the very least, we know it can work sometimes. And then we say, make our domain just polynomials. And, while we're at it, let's just throw in anything that could work. And so that gives you this. When you define the domain like this, it actually turns out to be, give us that the derivative operation is closed, which is pretty nice. And so but that's another property that we'll talk about another time, as for when we really want to dive into densely defined operators. Okay, let's see. Let's see. So my hourly check of the chat. Sorry, guys. So do I know Gödel's incompleteness? What do you think of it regarding learning analysis? Gödel's incompleteness is really irrelevant for learning analysis, honestly. I know it as much as the layperson does, probably a little bit better, but not a lot better. Just I've been to talks and heard people talk about it. I know what it is, but I've never really had to study logic at any point outside of just like basics of proofs. So it's kind of in its own field over there. There are implications in analysis, I should say that. But like as far as for your day-to-day work in analysis, it's not something you think about all that much. Which book am I using? My book. So I am throwing together a textbook on functional analysis and operator theory, and this is things I've sort of pulled together sort of from my own knowledge. But in the past, I mean, a lot of this content you'll also find in this. I've studied these guys, so Bionic Algebra Techniques and Operator Theory by Ron Douglas will have a lot of this content, and Real Analysis, Modern Techniques and Their Applications will also have a lot of this content. I particularly don't have anything on reproduced kernels. That's like stuff I pulled together from a variety of other sources. But that's that. And no, I don't mean, when I say Hardy space, I'm being very particular about the space I'm talking about. So if we go back here, the Hardy space is a particular Hilbert space. And it was defined in 1938 by Riesz, and it was given as this. How do I love the books? I love the books quite a lot. Honestly, I practically slept with this book for like years, for like months, years, honestly, like 2 years of just studying that book constantly, in both class, out of the class, referencing later for my research, things like that. My personal favorite, I bring it with me everywhere, is this guy. Actually, that's a good one too. No. I actually left my other book at home, but this one's actually a fun book if you want to check out this one. So if you want to learn sort of the Moore method for doing Hilbert space theory, he just gives you questions and you just answer the questions as you go. There is some overlap with reproduced kernel Hilbert spaces, etc. But a lot of these classical books don't really cover a lot of things in like machine learning is not really covered by any of them, or the reproduced kernel Hilbert spaces not really covered by them either. And so those you have to kind of go and dig around until you find them. So some of the resources I'm finding at reproduced kernel Hilbert spaces are one, the things I studied throughout my own PhD program. You can find books on the Hardy space that actually never even mention that's a reproduced kernel Hilbert space. But I think there's oh, darn, I'm blanking on it right now. Darn, I'll have to get back to you on that. But the Fox space has K.A.'s analysis on Fox spaces. It's a really good book. That came out in 2012, like right as I was wrapping up my PhD, which is sort of like it came in and saved the day for a lot of things I was doing. And the Paley Winter space, I can't remember what the book I was using for that was for. It was on Fourier analysis and sampling theory or something like that. I'll get back to you on that one too. Maybe next time when I come in, I'll be prepared with that. All right, let's see. So let's go ahead and so this are reproduced kernels. All right, so here we have our definition of a linear operator. Our definition of a linear operator basically says that given a Hilbert space, so this is a Hilbert operator on Hilbert space, you can define linear operators on other vector spaces. That's fine. I mean, in fact, any linear transformation that you saw in, say, linear algebra 101, that is an operator. And so basically we have this predefined like domain that we care about. When it comes to bounded operators, we're just going to declare the entire thing as our domain. But for the sake of future work that we're going to do in density defined operators and things like that, unbounded operators, we're going to look at this. And so basically this operator, it's linear, so it satisfies the superposition principle. And we have this one example from basic calculus, the derivative. And so we need to just have it mapping to a Hilbert space of some kind, and I chose the Hardy space for that. And I declared the domain to be all the functions where if you take the derivative, they stay inside the Hardy space. And so we can see that happens sometimes. So if you take any polynomial, or in this case monomials, and we can get polynomials through linear combinations, then basically if we take a derivative, this guy kicks out that n out there. That's kind of the culprit for why this is a problem, because there's no like upper bound for that coefficient that comes out of the front. And so then we can find a function that doesn't work, and that is this guy. And I think this is the logarithm, if I remember right. And so, but basically, we know that this guy, the coefficient is 1 over n. They're square summable. They give you pi squared over 6. Thank you, Euler, for putting that together. And then if we take the derivative, though, that n is going to come and cancel this n. It just leaves us with these coefficients that are just 1. And so then basically what we end up getting is if we try to see if these are square summable, the square sum of 1 is infinity, right? And so therefore f cannot be in the domain in D. And so we see that this operation doesn't define, the derivative operation isn't defined for all of the Hardy space. Yes, indeed. There is Dunford and Schwartz. Yeah, that was massive from what I saw. Like it was like these gigantic black books, if I remember right. A bunch of my friends had those when I was in a PhD program. I personally never really got through them myself. I just had a smattering of other books, and you basically just pick up what you need as you go. But yeah, Dunford and Schwartz, definitely a classic and very robust of a book. Let's see. Okay, so let's see. All right, so boundedness. Let's get into this. All right, so definition of a bounded operator. So a linear operator T mapping from H to H over a Hilbert space H is an operator that try to come up with this off the top of my head that satisfies that for which I should say there exists a C greater than 0 such that the norm of TF is less than or equal to C times the norm of F for all F in H. So a bounded linear operator. Bounded. Sorry, I forgot the key word there. A bounded linear operator. Let's make sure it shows up there. Yeah. So a bounded linear operator, T going from H to H over Hilbert space H is an operator for which there exists a C such that this happens. And so if you stop and think about what's going on here, F is some vector in your Hilbert space. You could even think of this as being Rn if you like, so an actual vector. a bounded linear operator basically is an operator that has a bound to how much is actually going to be scaling our vector. So it's going to stretch it out, but there's some sort of bound that it's not going to exceed. And so that's really nice. And then we say that LH is the set of all bounded operators. Okay, so it's actually pretty trivial to show that and it ends up giving you a vector space. You can go ahead and show that yourself. The fact that it's a complete space is actually maybe that's something we should show at some point, but today we're not going to get into that. But we define a bound on T. So for T inside of the collection of bounded operators, we say the norm on T is defined as this. So we have the norm of T is equal to the supremum for all F. Let's just say all F inside of H, and then we have TF divided by F. Or another way of looking at it, supremum for all norm F is equal to 1 of norm TF. So to get that one bit is actually pretty straightforward. You just see that every time you write this, you can just move that F inside as a scale, 1 over F, 1 over the norm of F, move it inside as a scalar, and then you just combine it with this guy to get something as norm 1. And so you're really kind of doing that. And so that is the norm. And so that the norm of TF is less than or equal to the norm of T times the norm of F. So we don't have to just deal with that C, but basically T is the smallest C that will work for all the F. And that's where that comes from. Okay, so we, after an hour of this, we've gone to what boundedness is. And so I guess I don't have a whole lot of time, but what I can do is I can go ahead and prove this following as equivalent statement. So, all right, so for an operator T going from H to H, a linear operator, the following are equivalent. All right, so we have one, that T is continuous. And with what I mean by continuous is the Hilbert space has a norm. That norm gives you a metric space, or it gives you a metric, which then gives you a metric space and continuity with those topologies. 2, T is continuous at 0. And 3, T is bounded. Okay, so what does this mean? Well, it tells us that it's equivalent to say that T is continuous and boundedness are the same thing. So the collection LH of all bounded linear operators is also a collection of all continuous linear operators. And so people in operator theory will use those interchangeably. And in fact, we almost never say an operator is continuous. We just say it's bounded, and then we just know what that means. It's continuous. I think, so it's not too hard to prove this. But basically, 1 implies 2. That's pretty obvious. If you are continuous everywhere, they're going to be continuous at 0. That's not too bad. Where's this coming from? Did I accidentally bump a thing? What is this? There we go. No. This is a text box. It's a text box. Sorry. I think I bumped something while I was writing. Just get rid of that. You know what? Fine. Just go away. Sorry. Okay. So, I'll figure that out later. All right. So, I'm just going to write clear. I hate writing clear, but there's literally, it's just by definition. So then we can get 2 implying 3. So continuous at 0. So we're going to suppose t is continuous at 0. And so then what we're going to get is we're going to get boundedness out of this. And so what we're going to do then is we're going to let epsilon be greater than 0 and select delta to be equal to it was like 1 over epsilon, or sorry, why did I choose? Sorry, it's like I wrote it down on the board. Let's see. Let's select delta so that the norm of tx minus t0 is less than epsilon for norm of x minus 0 less than delta. Or since t of 0 is 0, and since 0 is 0, that's basically saying that t of x less than epsilon for norm of x less than delta. Okay. So now I just need to come up with the right bound. And so we're going to, let's see, how am I going to do this? All right, so what we're going to need to do is we're going to take an arbitrary y inside of our h, and I'm going to shrink it down until it's inside of that delta ball. And so I then consider y divided by norm of y times delta over 2, which has norm less than delta, because y divided by norm of y has norm 1, and so then this altogether has norm of delta over 2, which is less than delta. So then we get the norm of t of y over norm of y, running out of space here. This we know is less than epsilon. And so what I can do then is I can multiply by the norm. I can take that norm of y out because of linearity and because of the norm, and I can take out and I can also take out delta over 2, and I can move them all over to the other side of the inequality. And so it tells us that the norm of ty is less than, let's see, it's going to be norm of y times epsilon over delta, and then times 2. And so this ends up being that c value that's greater than 0, because epsilon and delta are greater than 0. And so then, ta-da, you have boundedness. So this is arbitrary y inside of our Hilbert space, and so we got that t is bounded from the fact that it was continuous at 0. So now, what what can we do? What we have left is, so now I have 1 implies 2. That was pretty straightforward. 2 implies 3. We just did it. And so now let's see if we can get 3 implies 1, which isn't going to be too bad. So let's go ahead and add another page here. After there. So then let's get 3 implies 1. All right, so we have suppose T is bounded, and now we're going to get continuity. So we're going to say going to so we're going to let epsilon be greater than 0. And so what we're going to try to do is we're going to try to basically, it's actually going to be uniformly continuous, to be perfectly honest. So we're going to let epsilon be greater than 0 and select delta to be equal to say epsilon over the norm of t. So I'm going to take y naught inside of our h, and we're going to suppose that x minus for x and h, we have x minus y naught is less than delta. Then what we have is that tx minus ty naught, this is equal to t of x minus y naught by linearity. And this is less than or equal to, by boundedness, the norm of t times the norm of x minus y naught. But this is itself less than norm of t times delta, and that is equal to the norm of t times epsilon divided by the norm of t, because that's what we define delta to be, which is equal to epsilon. And so there we go. For an epsilon and a point in h, we have selected a delta. Turns out that delta doesn't need to change depending on what we change in h, and so it is actually uniformly continuous, which is pretty nice. But anyway, yeah. So that is, so we have 1 implies 2, 2 implies 3, 3 implies 1. So then in one big loop, they all imply each other, which is pretty nice. So that is the basics of the basic definition of boundedness, and boundedness gives us continuity, which is pretty nice. Now, I had some other stuff here I wanted to talk about. I wanted to go into the Banach algebra inequality, which we'll talk about next time. So it turns out that L of H is a Banach space, and it's a Banach algebra. And basically, if you have a Banach space that has a norm that satisfies this, that makes it a Banach algebra. And then I have examples I want to talk to you guys about with multiplication and composition operators. Composition operators, by the way, if you know anything about DMD or Koopman operators, that is basically what a Koopman operator is a composition operator. Then we're going to get into the definition of adjoints, and then we're going to prove that the adjoint of a bounded operator is itself bounded. But not all adjoints are necessarily bounded. The definition we're going to have will encompass sort of unbounded operators and things like that. And then after that, I was going to give a couple examples for the Fock space and the Hardy space, and I think that's where I was planning on ending, but I guess I just jabbered too much. Anyway, but I don't want to overload everybody. I don't want to take everybody else's time too much, and so we can just pick that up next week. So yeah. But yeah, I think boundedness and continuity, the fact that they're interchangeable is really cool. It's just a really nice property of linear operators, and I don't. I live and breathe. I get this nice cozy feeling whenever I'm working with like operators and boundedness and all this other stuff. It feels like going home. Basically, I spent, you know, like all my grad school just like studying this stuff constantly. So it was a lot of fun. Our bounded, yeah. So basically, the bounded operators are more or less uh, the linear transformations that satisfy the Lipschitz continuity. Yeah, it's just Lipschitz continuity here is just pretty trivial, because of the linearity property. So we just don't talk about that much. But yeah, but if you have the same thing but for a nonlinear operator or a nonlinear transformation of some kind, then we would really care about that Lipschitz property. Cool. No, they don't clap for us, clap for me. Though I do get a few thank yous and hey, good lecture, things like that is very nice. Yeah, I like my students, but yeah, no clapping. Thankfully, also no throwing of rotten tomatoes, which is also very positive. I mean, especially when you're teaching like a calculus one class, it might be full of people who really don't want to be there, and so they're just kind of happy that the lecture's over. But yeah, so we'll go over the other stuff next week, and yeah, but yeah, thank you guys for coming. I really appreciate having you guys. Way more people showed up than I expected, and yeah, let's try and make this a regular thing. I try to start at 11. Today I kind of had a road bump with a lot of technology issues. It took me like 30 minutes, 45 minutes to get that hammered out, but yeah. Anyway, so I'll have a video coming up on my channel for the Hermite function. Hermite functions as a basis for L2. That should be up tomorrow or Friday. And I'm also starting up a newsletter, and there'll be more of that stuff in the next video. I can talk about where I can send you snippets from the book I'm writing, code snippets, other things like that. So yeah, just keep an eye out for all that stuff. I don't know enough physics. I do math only. I bumped into physics here and there. I can say one or two things that are correct, and I can say a lot of things that are incorrect about physics, but that's about all I know. But yeah. All right, guys. So I'm going to go ahead and sign off. Thank you, guys, and